This nutshell gives programming exercises using the ADC. There are 3 problems: wind direction, battery level indicator, and garden watering timer, and I will get you to develop both the state diagram and code for that, and structure diagram and code for that. So it's an excellent way to practice your programming skills. And if you do find these nutshells useful, please like and subscribe. This problem is a wind direction indicator. The wind direction is connected to the ADC1, and we have 4 LEDs to show what the wind direction is, shown here. So I want you to pause the video and try and write the pseudocode and the state diagram for this problem. So pause the video now. My initial attempt, I have reworded the problem here and put the pseudocode into here, and I have shown the state machine here. Now the issue that this has is that the wind sensor will be a continuous sensor. So if I'm going to go from north to west, I have to temporarily go through 2 incorrect states. So then I need to rewrite the state diagram to compensate for this. I have shown it here. So now it's a lot more complicated, you can see. So basically we can move between any state depending on the wind, rather than going through the transition. And this is the pseudocode here. So pause the video now and try and write the state diagram into C code. So this is the code that I wrote for the first simple state diagram. We can see how we have 4 states shown here to find the outputs, and then we have a switch statement that we move through for the different states. I have then written the more complicated system shown here, and if we look on the main here, shift that down a bit, we can see we still have 4 states, but we have conditional statements going to our other states shown here. So this is a more robust state diagram. I have written the code and have downloaded it to the MicroPro board. We can see it in operation. Our wind sensor is on this pot, and our wind indicators are shown here below. And as the wind sensor changes, the wind indicators show the corresponding wind direction. This problem is a wind direction indicator. Read the problem and then pause the video and write the pseudocode and the structure diagram. So pause the video now. I have written the pseudocode and the structure diagram for this problem, and it involves an if-else ladder. Now pause the video and write the C code in Microchip Studio. You can see here the C code for this problem. I defined north LED on, west LED on, etc. shown here. In the setup, I have configured it VREF for AVCC, left adjust, and chosen the ADC1. And here I've turned the ADC on, started the conversion in free running mode, and I've got the clock divider at 128, and we can see our if-else ladder here. I have written the code in Microchip Studio and downloaded it to the Mega Pro board. So along here we can see these are our wind direction indicators, and our wind direction sensor is P1, ADC1, sorry. So therefore, if I were to change the direction, we can see the wind indicator changing, showing which direction the wind is coming from. When you have finished your state machine and your structure diagram, I'm just going to now compare the two systems. So if we scroll down here, we can see the structure diagram is very simple and elegant, whereas the state machine is actually quite complex and cumbersome. So sometimes state machines are really good, and sometimes structure diagrams are even better. This depends on the type of problem that you're doing. Have a look at this problem, then pause the video and write the pseudocode and the state diagram for the problem. So pause the video now. For my state diagram, I had three states: green, orange and red. We transition to orange if the voltage goes below 4 volts. We go back to the green if it goes above 4, or we go to the red if it goes below 3.5. And then if we're in the red, if it goes above 3.5, we go to the orange. So you can see the state diagram here. Finally, when we are looking at the conversion, I'm going to look at ATCW for 10 bits. We can use this formula here to calculate that at 4 volts, the ADCW will be 819, and at 3.3 volts, it will be 717. So now, pause the video again and see if you can write in Microchip Studio the code for this state machine. You can see the code now. There's defining the outputs for the green, orange and red LED, ADCW for the battery voltage, and our states shown here. We come into our different states, green LED on, and then we will change the states depending on the voltage level. And finally, we can see the setup here, the ATmux and the ADC SRA for reading the battery voltage. I have written the code and downloaded it into the Mega Pro board. I'm using the display driver to show the battery voltages. So we can see it running here now. Currently the battery voltage is high. As the battery goes down lower, we can see that the indicator here for the good battery level is on. As we go down below 4 volts, the marginal indicator comes on, and finally when we go down below 3.5 volts, the poor voltage indicator comes on. So you can see the whole thing indicating clearly. This is a problem about a battery indicator. So pause the video, read the problem, and write the pseudocode and the structure diagram. So pause the video now. So the problem in the actual fact is a simple if-else ladder. We come through here. If the battery voltage is greater than 4 volts, turn the green LED on and hop out of the if statement. If this is false, then we check to see if it's greater than 3.5 volts. If that's true, we do this. If that's false, then the red comes on. So have a look at that, see if you can understand it. Also, and I'm looking at here, I'm trying to work out what 4 volts is for the ADCW. It's 819, and 3.5 is 717. So now pause the video and see if you can write the C code. So pause the video now. So this is the C code. We have to find our LEDs. We're using ATCW for 10-bit ADCs, and we have the if-else structured ladder here. And we can see how we've set up the ADmux and the ADC SRA for this problem. I have downloaded this code into the MegaPro board. I'm also using the display to output battery voltages and the ADCW. So we can see that in action. Here we have the system running. We have the sensor here, and as the voltage goes down, we can see it saying good here. As it gets down below 4 volts, we can see now it's saying marginal, and when it gets down below 3.5, we can see that it's gone poor. So we can see the code working with the structure diagram. I'm going to show you a comparison between the state diagram and the structure diagram for this problem, but if you haven't yet done these problems, you might want to jump this section. So we can see the comparison. Here's the structure diagram here, here's the state machine here. State machines are very good, they're very powerful, but they don't always produce the most efficient code. We can see here that the structure diagram was a lot easier to implement. So just be aware of that. Read the description of the garden watering system, then pause the video and try to write some pseudo code and the state machine for the system. So pause the video now. When I look at state diagrams, I tend to look at the outputs as separate states. So when you do your state diagram, don't make them more complicated than they need to. They're just giving a description. But we have two states. The water's off, and when the dial's pushed, we go to the run state. And then in the run state, water's on. If the dial is pushed or time finished, we go to the stop state, as shown here. Some background information. We need to use a 10-bit ADC to give a set time. I need to look at this time finished in more detail, looking at the code, and debounce required on the buttons. Now, pause the video and write the C code for this state machine. You can see the C code as the state machine. The I/O are defined. Set minutes, looking at ADCW divided by 10. Two states, stop and run. We're initializing these variables, and then we're basically using a switch. Case state stop, water off. If button pushed, I had some debounce going on here. State goes to run. In state run, water's on. We reset the used minutes, and then I'm using this delay here to count up minutes, and that's compared with the set minutes. So we can exit this while loop here and then go back to state stop. And this is the ADC setup shown here. I have written and downloaded the code into the MegaPro board. I have included the display drivers so we can see what the ADCs are doing, our used minutes and set minutes. And I have put the time to 1 millisecond rather than 100, so the time will increment faster. So it's downloaded and running. We can see that we can change the time from 0 to 109. Set it down somewhere closer. Say 10. So if I start the push the dial, then the pump comes on. We can see that PC7, time gets to 10, and then the pump goes off. Start it again, and then I want to stop it manually, push it, so we can see the program is working. The garden watering system is shown here. Pause the video and then read the problem, write your pseudocode, and write your structure diagram for the problem. So pause the video now. The pseudocode, basically, if the dial button is pushed, turn the watering on and wait until either the timer is complete or the dial is pushed again, and then turn the water off. So if we look here, we can see if the button is pushed, water goes on, we clear this minutes variable, and we stay in this while loop, updating the minutes and staying there until either the time is expired or the button is pushed, water goes off. Some things to note: we'll use the Timber ADC. We need to refine this delay here and debounce the required buttons. So pause the video now and try to write the code. This is my final code for the structure diagram. We define our GPIO. We divide in the ADC W, which is the both bytes, high and low, by 10. We're having these variables here, use minutes and time seconds. If the dial is pushed, we do some switch debounce here, we turn the water on, we clear the count, and we stay in this while loop while the dial's not pushed and the use minutes is less than the set minutes. I've got a 100 millisecond delay here, so we will need 600 counts to get to 1 minute. So therefore we increment the use minutes after 600 counts. And then when we exit the while one, we actually have another debounce, water off. And you can see how I set up the ADC here. I have downloaded the code into the Mega Pro board. I am using the display so we can show the set minutes and use minutes. Also, I have shifted the delay milliseconds from 100 to 1 so that we can speed up the process. So we can see the code in action. We have the dial here to set the number of minutes that we're going to use. I'll set it down to a lower figure. Let's say 9. So then if I start the garden watering system, we can see the solenoids come on, and when it reaches the required time, the watering system turns off. If I start it again, and I push the dial a second time, the watering system goes off. So we can see it's working perfectly well.